Welcome back. This is an Aleks training video on understanding that no reaction goes to 100% completion. All right, so in this example, we have nitrogen gas and hydrogen gas coming together in a 1-to-3 relationship to form ammonia. So if you have for every 1 mole of nitrogen gas and 3 moles of hydrogen gas, it comes together and forms a product called ammonia, and you're going to get 2 moles of ammonia. What is true about every reaction is that when you get this ammonia itself can break down. Now look at the bottom equations. I've got two balanced equations at the bottom. This is just the one that we're using from this example, and it's backwards, okay? For every reaction that you can give me, I can give you a backwards one. Okay, if you say that nitrogen gas comes together with 3 hydrogens to form ammonia, I can say, well, ammonia can break down into nitrogen and hydrogen. Okay, and it's true. Everything can be broken apart that can be made. That means there is a reaction that can break apart things. There is a reaction that can make things. All right? Well, if you were to tell me that, I would immediately say, well, how can anything be made? If you make it and then it just undoes again, why would you ever see something? Why would you ever see anything that you could make? Because it would just undo it again. Okay? Well, here's the reason. If I were to go to the right and all of this nitrogen and all of this hydrogen would become ammonia, and then the ammonia wouldn't go back, then you'd have ammonia. All right? Yeah? Or if you had some ammonia and it would always break apart into nitrogen and hydrogen, then there would never be ammonia because ammonia would always go away. Well, what's happening is that both are true. Every time that 1 mole of nitrogen encounters 3 moles of hydrogen with sufficient energy, they will come together to form 2 moles of ammonia. And every time that you end up with 2 moles of ammonia with sufficient conditions, it will degrade or break back apart into nitrogen and hydrogen. What you see is that the amount that you're going to see in reality is based upon how the rates, how fast that these reactions are happening at the same time. Okay? So I want you to imagine a room full of paper wads, like wadded up paper. And I've got the 3rd grade on one side and the 2nd grade on the other side. And every time that you throw me a paper wad, we're going to throw it back. So I throw the paper wads, the 2nd grade throws it to the 3rd grade, and the 3rd grade picks them up and throws them to that, and everybody's throwing paper wads back and forth and back and forth. Anytime that I would say stop and count the paper wads on both sides of the room, then whoever is throwing faster is going to have more paper wads on the other side. Whoever's throwing slower is going to have more paper wads on their side. Okay? That's exactly what's happening with the nitrogen, hydrogen, and ammonia. Ammonia is being made and broken apart, but they're being made and broken apart at different rates. Remember the energy of action, the activation energy, the energy required to make it go one direction is not always going to be exactly the same height. It's not going to be just as easy. Let's look at the top arrows. If the activation energy were just as easy to go from right to left, then you'd end up with the same amount. Okay, so let me write that out. Let's say I have activation energy like this. Okay, so reactants, products are on the same level, and the activation energy is the same height. So if I go right to left, that's just as easy as going left to right. Well, what's going to happen, that would be the 2nd and 3rd grade are throwing at exactly the same rate, and I say stop, and I've got the same amount on both sides. I'll have the same amount of reactants, the same amount of products. Okay, they're going to be made at the same rate. What if the rates are different? What if the 3rd graders can throw harder than the 2nd graders? What if the backwards reaction, okay, the backwards reaction has an easier hill to climb across? Okay, then its rate is going to be faster than the forward rate. Fewer of these paper wads are going to go over the hill because the hill is taller on the front side than it is on the back side. you're still going to have some go over. Even though the ammonia may break apart into nitrogen and hydrogen, some of it may still go back. So you're never going to get, it's never going to go forward completely to the right or completely to the left. And what about the other one? The other one, you're going to have a high mountain on this side and a low mountain on the other side. Okay, so it's easy to go right to left or left to right. It's harder to go backwards because the hill is harder on that side. Okay, so the rates are different. So when you go forward, some of it's going to go back, okay, or lots of it's going to go back. Okay, so it's a war. It's a war between rates, but you're never going to go forward completely or backwards completely. Okay, so let's answer the question. I've got 135 millimoles of nitrogen, 405 moles of hydrogen. That happens to be a 1-to-3 relationship. Okay, so we have a 1-to-3 relationship. That means that when you have a 1-to-3 relationship, you're going to start going forward and making some ammonia. So if you put that in an empty flask and it starts, the reaction starts, how much nitrogen will be in the flask after it equalizes? Okay, after the same rates, everybody's throwing it however hard they can throw. That's the equilibrium. Okay, then how much nitrogen will be in there? Well, none would mean that this forward arrow was complete and there was no blue arrow at all. None was coming back at you. Okay, so it can't be that because there is a blue arrow. There is something coming back at you. 135 millimoles would mean that none came back at you. Okay, so it can't be 135. It can't be more because you can't have more than you started with. It has to be some. It's number 2. It has to be some, but it's less than you started with because some of it's being made into this and some of it's coming back. So there will be some nitrogen, but just not as much as you started with. So the answer here would be some but less than 135 moles. What about the second one? The second one says, suppose you have 100 millimoles of ammonia. So you're going to start over here with 100 millimoles of ammonia. Okay, and it's going to start breaking apart into nitrogen and hydrogen. How much nitrogen will be in the flask at equilibrium? Well, go back to the balanced equation. 2 ammonias break apart into 1 nitrogen and 3 hydrogens. So for every 100 millimoles of nitrogen, or ammonia, you should get 50 millimoles of nitrogen if it went 100% to the left. Well, it's not going to go 100% to the left because as it's going left, that nitrogen hydrogen's combining and going right. Okay, so you're going to get some. You're just going to get less than 50. Okay, because it went completely to the left, it went completely from ammonia to nitrogen, you'd get 50. Okay, because I started with 100 and it's a 2-to-1 relationship, so I'd get 50. But I'm not going to get all the way to 50 because some of the forward reaction is going to make ammonia again. Okay, so that's the idea. You have to it's a war going back and forth and back and forth. Okay, so fight on.